Hi, I'm Sala, and in this video, we'll continue with the intuitive understanding of what the Vinnicombe's no-gap metric means in a real-valued single input, single output case. In other materials, we learned that if we have a plant P1, which is represented as some numerator and denominator, normalized, in the real case, this can be understood as something like numerator squared plus denominator squared equal 1. Then, if the real plant is P2 with some disturbance on this numerator and denominator, if the infinity norm of the uncertainty of denominator and numerator just juxtaposed is lower than this margin, then we can guarantee robust stability. As we were discussing just a single input, single output case, and this numerator and denominator even being real, not even complex, then okay, this stuff is just the norm of a vector of uncertainty, which, as we discussed in a previous video, any number expressed as a fraction, numerator, denominator, can be understood as a pair of numbers that are equivalent, representing the same number, if the quotient is the same. So all points in the blue and red lines represent the same real number, and the normalized representation of P1 and P2 are the green and red stars, respectively. It has this form for P1 and, of course, this form for P2. Then the distance in normalized factorization with minimum norm of this kind of uncertainty description is the length of this segment, because that transforms the normalized representation of P1, D1 and 1, onto something which is on the line that represents the disturbed plant P2. This length is actually the sinus of the angular difference between the two lines. So now we will just replace P1 and P2 normalized by these expressions, and we'll do further computations to get an expression of this sinus as a function of the real numbers P1 and P2, and not of this two-dimensional abstract stuff which is the normalized factorization. So let's go. For the development, we need the well-known formula that the scalar product of two vectors in R2, which is x1 transposed x2 if we represent them as columns, is equal to the product of the Euclidean norms times the cosine of the angle between them. And if we are dealing with normalized representation, then I can just forget about this and say that the scalar product is the cosine of the angle. So if this is norm 1, the scalar product will be the length of this segment. The problem is that we need to obtain an expression for the sine of this angle, but the sine of an angle is the cosine of the complementary angle, the cosine of 90 degrees minus alpha. So we need to think on a perpendicular vector to the red line, this one. So this thing will be 90 degrees minus alpha, and hence the length of this cyan line must be equal to the length of the dark blue one, if correctly drawn, okay? But how can we get a vector forming 90 degrees with this point? Well, it's easy. It's well known that if I reverse the order and change sign of one of them, then I get this orthogonal unit norm vector and the pink arrow. So the scalar product of this orthogonal vector with this thing will give me the required sinus. Then this is it. If we have D1 and 1 and D2 and 2 normalized, then I rotate 90 degrees with this, I get that vector, and the scalar product is just the first one times first one plus second one times second one, it's this expression. So the length of this line, and this one of course, is the absolute value. We are just measuring a length, we don't want the sign of this expression. So this is the normalized expression for the nu gap. Then, if we have P1, the nominal plant, and P2, the disturbed plant, described as P1 over 1, P2 over 1, and with this normalized representation, this thing will be denominator 1, this thing will be nominator 1, and here D2, N2. Carrying out these operations, we get that D2 times N1 is just P1 over this product of square roots, and D1 times N2 with changed sign is minus P2 divided by this product of square roots. So the overall expression is this one, and if we take the positive square roots and the absolute value of the difference between the real numbers, P1, P2, then we get this expression of the nu gap in unnormalized original coordinates. So this is how to compute an actual numerical value of the sign we described in this slide. Good. We will now discuss a second geometrical interpretation, which is actually the one presented in the seminal reference about all this. That second interpretation will be as a real distance, because this understanding of the sign of an angular difference is the underlying concept, but okay, we would like to understand the coprime factor uncertainty metric as a distance between something. Well, okay, that can be done, and that's what I will explain now. First, we need a preliminary result on angle duplication. If we consider this circle is half the size of the circle we were considering until now. So this is diameter 1, not radius 1, as before. So if we have a circle which is diameter 1, if this angle, we call it beta, then the length of this is 0.5, the radius, and of course, this is also 0.5, the radius. So this is an isosceles triangle, and then this angle will be also beta, and as the sum of the angles of a triangle is 180 degrees, then the red angle will be 180 minus 2 beta, and then this green angle is 2 beta. So taking first an angle between points with one of the sides being a diameter, if we start the line at the center, then the angle gets doubled. This is a well-known construction, but okay, I review it just in case. So we have this kind of duplication of angles. Then back to our original construction. Let us now consider the circle of half the diameter, and let us consider this point and this point. Well, the result will be that the distance between these two brain points will also be equal to the length of the blue segment. So this will be also sinus of alpha. Let's prove it. First, note that the lines here, red and blue, are exactly the same as the ones in the previous slide, but we just rotated 90 degrees. Okay, look, this is a distance of 1, and then P1 and P2 go over there. This is a distance of 1, and P1 and P2 go up there. So if we just rotate 90 degrees this figure and think of the dark blue circle, we get this. So this alpha is the same as we had before. Then with this angle duplication trick, this angle will be 2 alpha, because okay, the original angles beta 1, beta 2 will be duplicated, so the difference will also be duplicated. So this is 2 alpha, and now if we split that angle into halves, then this will be alpha, this will be alpha. So which will be the length of this upper half here? Well, the radius 0.5 times the sine of alpha, and likewise the length of the segment down here will be the same. So when we add those two lengths, here we have the main result. This distance d is also equal to the sine of alpha. Hence, this chordal distance, the green line here, has the same length as the sine of alpha that we originally had with a right angle. So this is the interpretation in Vinnicombe's papers. And even if it is harder to grasp at first glance than this minimum distance interpretation in sinusoids, the advantage is that it can be understood instead of as a distance between a point and a line, as a distance between 2 points. And these 2 points, in fact, are old friends in people in geometry, because this construction in which points in a line and in a circle or a sphere are related by a line that goes out from the north pole of a sphere, then this construction is called stereographic projection. So, in summary, the new gap, the normalized coprime factor distance between two planes, is the distance between the stereographic projections of them. So it's kind of a clean description, even if, of course, to deeply understand its meaning, we have needed to do a lot of intermediate steps. So let us summarize. Factorizations of a number can be assimilated to a straight line in a space in which we plot numerator and denominator in a plane. The normalized factorization is the intersection of those lines with the unit circumference. The minimum distance that converts a nominal plant into something equivalent to a disturbed plant, this delta, is the sine of the angle difference, but okay, we can write it as this, is we have the normalized expression, and if we have the original real numbers as the normalized expression, have the expressions down there, then we can write it like this in the unnormalized expression. And this distance between a point and a line can also be understood as the distance between the stereographic projection of P1 and P2, a chordal distance. Of course, these geometric interpretations must be generalized to complex values, because frequency response of plants is complex, and in fact to matrix, multidimensional stuff. That's done in the advanced textbooks, but our goal here was just getting a basic understanding with elementary geometry on the plane of the meaning of all this. This is it. Thanks for watching.